Dear friends, let us discuss the guides and criteria for locating ore deposits, stratigraphic, lithological, structural, geomorphological, paleogeographic and paleoclimatic criteria. What is ore geology? Unfortunately, it is not possible to give an unequivocal answer to this question. If one wishes to go beyond saying that it is a branch of economic geology, the difficulty is that there are a number of distinctly different definitions of ore. A definition which has been current in capitalist economies for nearly a century runs as follows. Ore is a metalliferous mineral or an aggregate of metalliferous minerals, more or less mixed with gangue, which from the standpoint of the miner can be won at a profit, or from the standpoint of the metallurgist can be treated at a profit. There are many similar definitions of ore which all emphasize that it is material from which we extract a metal, and B, that this operation must be profit making one. Economically mineable aggregates of ore minerals are termed ore bodies, ore shoots and ore deposits or ore reserves. The term strata bound is applied irrespective of their morphology to those deposits which are restricted to a fairly limited stratigraphical range within the strata of a particular region. For example, the vein, flat and pipe lead zinc fluoride barite deposits of the Pennine ore fields of Britain are restricted to the lower Carboniferous and therefore spoken of as being strata bound. To take a very different example, the stratiform deposits of the Zambian copper belt are all developed at about the same stratigraphical horizon in the Rhone series, and these two may be described as strata bound. Clearly, stratiform deposits can be strata bound, but strata bound ores are not necessarily stratiform. Two important associations will be dealt with here. Carbonate hosted base metal deposits and sandstone uranium vanadium base metal deposits. Coming to the carbonate hosted base metal deposits, these are important producers of lead and zinc and also sometimes principally of fluorite and barite. Copper is important in some fields, notably that of the central island. Coming to the distribution in time and space, most of the lead and zinc produced in Europe and USA comes from this type of deposit. In Europe, there are important fields in Central Ireland, the Alps, southern Poland and the Pennines of England. In the USA, there are the famous Appalachian tri-state, that is southwest Missouri, northeast Oklahoma and southeast Kansas, southeast Missouri and upper Mississippi districts. There are also important fields in North Africa, that is Tunisia and Algeria. Few deposits of this type have as yet been located in the Precambrian. Minor Mississippi Valley type mineralization, at least 2.3 giga-annums old, occurs in the Transvaal but the Guyana River deposits. Northwest Territory of Canada has more than 50 meters running up to 10% combined metals. It is, however, only 0.9 giga-annum old. Substantial deposits first appear in the Cambrian of southeast Missouri, and important deposits occur in all systems except Silurian up to the Cretaceous, as can be seen from the following examples. Cambrian southeast Missouri old and new lead belts, Ediacara, South Australia, Sardinia, Spain. Ordovician, upper Mississippi. Devonian, Pine Point, Northwest Territories, Canada, Leonard Shelf area, Western Australia. Carboniferous, Central Island, British Pennines, Tri-State, Illinois, Kentucky. Permian, Trento Valley, Italy. Triassic, Eastern Alps, Austria and northern Yugoslavia. Jurassic, southern Poland, also in Triassic and Devonian. Cretaceous, northern Algeria and Tunisia. Limestones are very common host rocks for base metal sulfide deposits. In a dominantly carbonate sequence, ore is often developed in a small number of preferred beds or at certain sedimentary interfaces. These are often zones in which the permeability has been increased by dolomitization or fracturing. When they form only a minor part of the stratigraphical succession, limestone, because of their solubility and reactivity, can become favorable horizons for mineralization. The ore zone consists of feldspathic sandstones, which in places contain carbon-rich lenses with much sericite. The basal portion is coarse-grained and characterized by festoon crossbedding, in which bornite is concentrated along the crossbedding together with well-rounded, obviously detrital zircon, whilst in other parts of the ore body, concentrations of sulfides occur in the hollows of ripple marks and in desiccation cracks. These features suggest that some of the sulfides are detrital in origin. Mineralization ends abruptly at the hanging wall, suggesting a regression, and at this sharp cut off, the facies changes from an arenaceous one to dolomites and shallow water muds. Alluvial gravels and conglomerates also form important recent and ancient placer deposits. Alluvial gold deposits are often marked by white runs of veen quartz pebbles, as in the white channels of the Yukon and the white bars of the California and the white leads of the Australia. Such deposits form one of the few types of the economic placer deposits in fully lithified rocks, and indeed the majority of the world's gold is won from Precambrian deposits of this type in South Africa. There are two principal types of deposits to be found in volcanic rocks: vesicular filling deposits and volcanic associated massive sulfide deposits. The first deposit type is not very important, but the second type is a widespread and important producer of base metals, often with silver and gold as byproducts. Many plutonic igneous intrusions possesses rhythmic layering, and this is particularly well developed in some basic intrusions. Usually the layering takes the form of alternating bands of mafic and felsic minerals, but sometimes minerals of economic interest such as chromite, magnetite and ilmenite may form discrete mineable seams within such layered complexes. Apart from some deposits of metamorphic origin, such as the irregular replacement deposits already described and deposits generated in contact metamorphic aureoles, for example of wollastonite, andalusite, garnet and graphite, metamorphic rocks are mainly important for the metamorphosed equivalents of deposits that originated in sedimentary and igneous rocks. It is possible to classify ore bodies in the same way as we divide up igneous intrusions according to whether they are discordant or concordant with the lithological banding or often bedding in the enclosing rocks. Considering discordant ore bodies first, this large class can be subdivided into those ore bodies which have an approximately regular shape and those which are thoroughly irregular in their outlines. If an ore body viewed in plan is longer in one direction than the other, we can designate this long dimension as its strike. The inclination of the ore body perpendicular to the strike will be its dip, and the longest dimension of the ore body its axis. The plunge of the axis is measured in the vertical plane ABC, but its pitch or rake can be measured in any other plane. the usual choice being the plane containing the strike, although if the ore body is fault controlled, then the pitch may be measured in the fault plane. Coming to the tabular ore bodies, these bodies are extensive in 2 dimensions but have a restricted development in their 3rd dimension. In this class, we have veins, sometimes called fissure veins, and lodes. In the past, some workers have made a genetic distinction between these terms. Veins were considered to have resulted mainly from the infilling of pre-existing open spaces, whilst the formation of lodes was held to involve the extensive replacement of pre-existing host rock. An initial fracture in rocks changes its attitude as it crosses them according to the changes in physical properties of the rock, and these properties are in turn governed by changes in lithology. When movement occurs producing a normal fault, then the less steeply dipping section is held against each other to become bearing surfaces, and open spaces, that is dilatant zones, form in the more steeply dipping sections. Then, should minerals be deposited in these cavities, a vein will be formed. If the reader carries out the experiment of reversing the movement on the initial fracture, he will find that the steeper part of the fault now act as bearing surfaces, and the dilatant zones are formed in the less steeply dipping sections. Veins are usually developed in fracture systems and therefore show regularities in their orientation. At the Sigma mine, cubic slab vertical gold quartz veins have formed within ductile shear zones during reverse movements caused by north-south compression. Where the shear zones crossed sub-horizontal fractures, tension veins were formed and then displaced by the reverse movement. Shear zones are commonly important locations of vein deposits and their development and complexities. Next is tubular ore bodies. These bodies are relatively short in 2 dimensions but extensive in the 3rd. When vertical or subvertical, they are called pipes or chimneys. When horizontal or subhorizontal, mantos. The Spanish word manto is inappropriate in this context, for its literal translation is blanket. It is, however, firmly entrenched in the English geological literature. The word has been and is used by some workers for flat-lying tabular bodies, but the perfectly acceptable word flat is available for these. Therefore, the reader must look carefully at the context when he encounters the term manto. Next is irregular shaped bodies and disseminated deposits. In these deposits, ore minerals are peppered throughout the body of the host rock in the same way as accessory minerals are disseminated through an igneous rock. In fact, they often are accessory minerals. A good example is that of diamonds in kimberlites. Another is that of some orthomagmatic nickel copper deposits such as La Perouse layered gabbro, Alaska, which contains disseminated sulfide mineralization throughout its entire thickness of about 6 kilometers. Next is irregular replacement deposits. Many ore deposits have been formed by the replacement of pre-existing rocks at low to medium temperatures, that is around 400 degrees Celsius, for example magnesite deposits in carbonate rich sediments, pyrophyllite ore bodies in altered pyroclastics, and siderite deposits in limestones. Other replacement processes occurred at high temperature at contacts with medium sized to large igneous intrusions. Such deposits have therefore been called contact metamorphic or pyrometasomatic. However, skarn is now the preferred and more popular term. The ore bodies are characterized by the development of calc silicate minerals such as diopside, wollastonite, andradite, garnet and actinolite. These deposits are extremely irregular in shape. Tongs of ore may project along any available planar structural bedding, joints, faults, etc. and the distribution within the contact areole is often apparently capricious. Next is concordant ore bodies, sedimentary host rocks. Concordant ore bodies in sediments are very important producers of many different metals, being particularly important for base metals and iron, and are of course concordant with the bedding. They may be an integral part of the stratigraphical sequence, as in the case with Phanerozoic ironstones, that is syngenetic ores formed by sedimentary processes, or they may be epigenetic infillings of pore spaces or replacement ore bodies. Usually these ore bodies show a considerable development in two dimensions, that is parallel to the bedding, and a limited development perpendicular to it, and for this reason such deposits are referred to as stratiform. The most important feature is the presence of a thick carbonate sequence, because thin carbonate layers in shales seldom contain important deposits of this type. The fauna and lithologies of the limestones and dolomite hosts show that they were mostly formed in shallow water near shore environments of warm seas peripheral to intracratonic or craton center basins, and a plot of major carbonate hosted deposits on paleo latitude maps shows a grouping of these deposits in low latitudes. Some ore districts, for example Naniswig, Canada, and the Eastern Alpine district straddling Austria, Italy, and Yugoslavia occur in former rift zones, and others occur close to carbonate shale facies changes. The warmer climates of low latitudes encourage the development of reefs, and so the frequent by no means universal association of these deposits with reefs. For example, southeast Missouri and carbonate mud banks, for example Ireland, is not surprising. The occurrence of reefs and carbonate mud banks is related to ancient shorelines and seabed topographies. Nowadays, along the shorelines where carbonate deposition is occurring, we often find arid zones, as in the Persian Gulf, with desert prograding supratidal flats or coastal subkhars. There, gypsum and anhydrite are precipitated from marine derived groundwaters to form evaporites. These may be of considerable significance. The isotopic composition of the sulfur or sulfides from a number of carbonate hosted deposits suggests origination from seawater sulfate, particularly seawater of the same age as the limestone country rocks. Sulfate evaporites are known to be interbedded with the limestones in relatively a close regional proximity to many carbonate hosted deposits. Thus, as Stanton 1972 has emphasized, the primary regional control of such deposits is paleogeographical. Environments such as these described above developed in the past along the margins of the marine basins that formed in stable cratonic areas, such as the Devonian Elk Point Basin of Western Canada, in which the Pine Point deposits occur. Next is carbonate hosted. Carbonate hosted lead zinc deposits also occur in a very different environment in the failed arms, that is olacogens of the triple junctions of rifted continental areas, as in the Benue Trough and the Amazon Rift Zone, and on the flanks of embryonic oceans, as down the flanks of the Red Sea and the Tethys Ocean or Alps. In this environment too, there is an important development of evaporites. A negative but important point is that these lead zinc deposits are remote from a post-host rock igneous intrusive, which might be the source for mineralizing solutions. Returning to the cratonic basin shelf sea environment, we may note other regional controls which are well exemplified by the Mississippi Valley region and the British deposits. In these regions, the ore fields are present in positive areas of shallow water sedimentation and separated from each other by shale-rich basins. Such positive areas in the British Isles are often underlain by older granitic masses, and Evans and Maroof 1976 suggested that these very competent rocks fractured easily to produce channelways for uprising solutions, which on reaching the overlying limestones gave rise to the mineralization. In addition, a large number of deposits are clearly related spatially to faults, sometimes of a regional character, up which the ore solutions may have passed. Sometimes the material left behind has been sufficiently concentrated by weathering processes and groundwater actions to form residual ore deposits. For the formation of extensive deposits, intense chemical weathering, such as in tropical climates having a high rainfall, is necessary. In such situations, most rocks seed a soil from which all soluble material has been dissolved, and these soils are called as laterites. As iron and aluminium hydroxides are amongst the most insoluble of natural substances, laterites are composed mainly of these materials and are therefore of no value as a source of either metal. Sometimes, however, residual deposits can be high-grade deposits of one metal only. The genesis of lateritic bauxite deposits is governed largely by the cumulative effect of several controls, and important among them are a favorable parent rock with easily soluble minerals whose leaching will leave a residual enrichment of aluminium and or iron. B. Effective rock porosity allowing free circulation of water. C. High rainfall with intermittent dry spells. D. A good drainage. E. Tropical warm climate. F. Low to moderate topographical relief. G. Prolonged stability. And H. Presence of vegetation including bacteria. Since manganese is more mobile than iron, the problem arises as to why manganese is retained in the weathering profile. The reason is probably because in most cases the residual manganese deposits are formed on low-grade manganiferous limestones and dolomites. These rocks are low in iron and silica, and manganese takes the place of iron in the laterite profile. The carbonates are easily dissolved by comparison with silica, and a higher pH that probably prevailed in these environments would have tended to immobilize the manganese. High level or upland bauxites. These generally occur on volcanic or igneous source rocks, forming thick blankets of up to 30 meters, which cap plateaus in tropical to subtropical climates. Examples occur in the Deccan Traps of India, southern Queensland, Ghana and Guinea. These bauxites are porous and friable, shows a remarkable retention of parent rock textures, and are dominantly gypsitic. They rest directly on the parent rock with little or no intervening underclay. Bauxitization is controlled largely by joint patterns in the parent rock, with the result that chimneys and walls of bauxite often extend deep into the footwall. Next is low-level peneplain type bauxites. These occur at low levels along tropical coastlines such as those of South America, Australia and Malaysia. They are distinguished by the development of a pisolithic texture and are often bohemitic in composition. Peneplain deposits are generally less than 9 meters thick and are usually separated from their parent rock by kaolitic underclay. They are frequently associated with detrital bauxite horizons produced by fluvial or marine activity. Next is the karst bauxite. These include the oldest known bauxites, those in the lands just north of the Mediterranean, which range from Devonian to mid-Miocene. Other major deposits are the tertiary ones of the Jamaica and Hispaniola. These bauxites overlie a highly irregular karstified limestone or dolomite surface. Texturally, karst bauxites are quite variable. The West Indian examples are gypsitic ores with structureless, earthy, sparsely concretionary textures. European karst bauxites, on the other hand, are generally lithified and texturally piezolytic, oolitic, fragmental, or even bedded. Mineralogically, they are predominantly boehmitic ores. From these and other facts, Grubb contended that the West Indian bauxites have strong affinities with upland deposits, whilst European karst bauxites are more reminiscent of peneplain deposits. Next is transported or sedimentary bauxites. This is a small class of non-residual bauxites formed by erosion and redeposition of bauxitic materials. Ore deposits carry a family of indicators including stratigraphic, where a particular mineral of interest is part of a specific strata having a defined age. The lithology criteria points an ore confined to a special lithology, while sometimes it can be localized in a deformational structure. Some geomorphological and or paleogeographical situations may also favor the ore concentrations in a few cases. Paleoclimate too plays a vital role in the concentration of an ore deposit. Thank you very much.